Hello, welcome to my talk. I'm Michał Włodarczyk, and I'll be talking about joint work with Bart Jansen on Lossy planarization, a constant factor approximate kernelization for planar vertex deletion. Before moving to the problem in question, let me start with a slightly bigger picture. First, recall what is a minor relation in graphs. So one graph is a minor of another if it can be obtained from the second graph by a series of edge or vertex removals or edge contractions. In this example, by removing the gray vertices and edges and contracting the black edges, we can obtain the graph on the right. Now, for any finite family of graphs F, we can define the problem F minor phi deletion, where we're given an undirected graph G, an integer K, and we look for a vertex set of size at most K, so that after removing these vertices, the graph doesn't contain any graph from F as a minor. There are numerous examples of problems that can be expressed in this formalism, in particular vertex cover or feedback vertex set. For example, in feedback vertex set, we want to hit all the cycles in the graph, which is equivalent to hitting all K3 minors. In the planar deletion, we want to remove at most K vertices from the graph to make it planar, so to make it embeddable on a plane without crossings. By Wagner's theorem, this is equivalent to hitting all the K5 minors, where K5 is a click on 5 vertices, and K33 minors, where this is a complete bipartite graph. Another examples include outer planar deletion or tree-width eta modulator, where we want to remove vertices to reduce the tree-width of the graph. There is one important special case for F minor phi deletion, which occurs when the family F contains at least one planar graph. We know that this is equivalent to a condition that all F minor phi graphs have tree-width bounded by some constant. For this special case, there is a powerful meta-theorem by Fomin, Lokshtanov, Misra, and Saurabh, which states that whenever F contains a planar graph, then F minor phi deletion admits a constant factor polynomial time approximation, a polynomial kernelization, and a single exponential FPT algorithm. What is important is that for all these three algorithmic benchmarks, the condition that F contains a planar graph seems to draw a boundary of our understanding, in a sense that we don't know any other family F outside the special case for which we would have any of these three desirable kinds of algorithms. Now, planar deletion is arguably the simplest example of a F minor phi deletion problem, which is not yet understood. Planar graphs have unbounded tree-width, so they don't fall into this category, also because neither K5 nor K33 is planar. So for this case of planar deletion, the state of art is as follows. For the approximation, we know n to epsilon approximation in polynomial time for any positive epsilon, and polylog n approximation in quasi-polynomial time. When it comes to polynomial kernelization, we actually don't know anything, and this is a very big open question in the area. When it comes to exact FPT algorithms, there is an algorithm with running time 2 to k log k, which is pretty close to the lower bound to O of k, but still there is some gap. My talk concerns the the area in between the item 1 and item 2. So I'll be talking about something in between approximation and kernelization. Let me now introduce the framework in which we work. Recall that in the standard kernelization, we look for a polynomial kernel for a parameterized problem. So a polynomial time algorithm that takes instance gk and produces an equivalent instance on of size polynomial in terms of parameter k. This can be interpreted in such a way that whenever a parameterized problem admits a polynomial kernel, then solving small instances of this problem entails solving instances with a small solution. For problems which are hard, both from the perspective of kernelization or approximation, Lokshtanov, Panolan, Ramanujan, and Saurabh proposed a framework of Lossy kernelization or approximate kernelization. Lossy kernelization is a pair of algorithms. First one is a compression algorithm that takes instance gk and produces an instance of size poly k, not necessarily equivalent. And the second one is a lifting algorithm that takes some solution to the compressed instance and translates it into a solution to the original instance in such a way that solutions which are good approximations here are being translated to good approximations there. This can be compared to the standard kernelization in the following way. So now when we have Lossy kernelization for some problem, then when we are able to solve small instances just approximately, this implies solving instances with a small solution also approximately. Another way of looking at this is as follows. So in a standard kernelization, the relation between optimum and the parameter k is preserved. If we're interested in constant factor approximate kernelization, then whenever optimum is smaller than is at most k, then the compression algorithm shouldn't increase the optimum too much. It might increase it by some constant factor, and the lifting algorithm also shouldn't increase the size of the solution too much. And if we are able to solve the small instance with a constant factor approximation, then by following this route, we can also have a good approximation for small solutions in the original instance. After this introduction, I'm ready to present our main result, which says that planar deletion problem admits a deterministic constant factor approximate kernelization of polynomial size. For me, the main importance of this result is that while planar deletion might seem hard for a kernelization framework alone and hard for approximation framework alone, we show that it is amenable to the both frameworks together. Apart from this conceptual message, we get a direct corollary for standard approximation. So after running our approximate kernelization, we can apply the state-of-art approximation algorithms to the compressed instance. In the compressed instance, the size of the graph becomes polynomial in the optimum. So when the approximation factors were expressed in terms of the size of the graph, now they become expressed in terms of the optimum. And let me note that prior to our work, even the existence of poly-opt approximation for planar deletion was open. let me now sketch the main ideas of the algorithm and the proof. The first preprocessing phase ensures that whenever a graph has a solution of size at most k, then we can find a planar modulator x of size poly k with additional convenient property that for every connected component C of G minus X, not only the graph induced by C is planar, but also graph induced by C together with its neighborhood. So for any such subgraph, we can consider some plane embedding of C plus its neighborhood with the vertices from the neighborhood marked as terminals. Our strategy is now to process each subgraph independently, and in each of them marked some green vertices, so that for any solution, if this solution deletes some vertices which are not marked, then every such vertex can be replaced with a constant number of marked vertices. This means that when we take a union of all the marked vertices together with the modulator x, we get a vertex set that covers an approximate solution. Now the remaining task is to compress the leftover subgraphs in such a way that later on the lifting algorithm could translate good solutions to good solutions to the original instance. But because we can treat these subgraphs as undeletable with respect to the approximate solution which lives in the marked area, we can now apply some known techniques. And the most challenging part of the algorithm is in this marking scheme to cover an approximate solution, and I will focus on this part now. Let us take a closer look on a planar subgraph with its neighborhood marked as squares. We can treat this entire subgraph as a boundaried plane graph because we have a plane embedding for the subgraph, and the square vertices are the boundary because these are the only vertices that can communicate with the rest of the graph. Now our task is to understand the following process. After removal of the optimal solution in the entire graph G, we obtain some planar components which are connected to the graph H only via the terminals. And in this picture, this remaining graph that is being glued to H is depicted in gray, and we want to understand what kind of removals within H we need to do in order to accommodate both the white graph and the gray graph together on a plane. If we identify such vertices which are sufficient to be deleted within H, then we know that there is some solution that uses these vertices in some approximate solution. In this example, we see that in the gray graph, the terminals might live on different faces. So when we want to make a common drawing for everybody, then we might need to separate these terminals from each other in the white graph in H. So this task generalizes multi-way cut on planar graph. This problem actually does admit polynomial kernelization, but our task is slightly more difficult. In the next example, we see that sometimes we don't need to separate terminals from each other, but sometimes we just need to remove some vertices so that we can rearrange the embedding. So that, for example, here the terminals A, I, D can be drawn closer to each other. So this little gray component can be drawn in the middle. And without deleting the vertex tree, it would be impossible to accommodate the gray component together with the white component. On the last example, we see that removing the vertices 2 and 4 makes the vertex tree an articulation point. And now we can tweak the embedding of H by pivoting around the vertex tree so that the order in which these terminals are embedded is different than the original order. And this might be necessary to connect them in a coherent way with the drawing of the gray graph. Let me move to our marking scheme. So this is a schematic drawing of some planar graph with a set of terminals. So the terminals are the only vertices which might be connected to the outside world. The initial reductions and marking scheme allows us to mark additional set of poly-K vertices. So now the gray subgraph is split into several regions so that each region communicates with the rest of the graph only through its outer face. In the next step, we look for sparse cuts in this smaller subgraphs. So cuts that are relatively small and separate two large sets of terminals from each other. And we add these vertices in these cuts to the marked set, and we continue as long as we can find some sparse cuts. We show that after poly-K many steps, this process must terminate, and now every small graph, so for example this one with a boundary on its outer face, is so balanced, so rigid, that whenever a solution would remove some vertices within the gray area, this would affect only a small number of the boundary vertices. In particular, we can find some set of boundary vertices here of size proportional to the initial removal set, which simulates these removals inside. And this is exactly the marking scheme that we look for, because any deletions in this potentially large gray set can be now simulated with a similar number of deletions only in the colorful vertices, which are like only poly-K, many of them. So let me go back to the previous picture, and this is what I just sketched, the marking scheme of the gray vertices, of green vertices that cover an approximate solution. I decided to focus on this part because we conjecture that this is really the bottleneck for understanding the compressibility of planar deletion. And if one wants to improve the approximate kernelization and exact kernelization, this is exactly the sub-problem that needs to be better understood. The setting with planar subgraph with terminals on the outer face. And if we want to get an exact kernel, we would need a marking scheme to cover not an approximate solution, but an exact solution. Let me conclude with two open problems. So the question whether planar deletion admits an exact polynomial kernel remains a main open problem in the area, and we believe that better understanding of this marking some problem on single-phased boundaried subgraphs would also help us in like understanding the exact compressibility of planar deletion. Secondly, we showed an approximate kernelization for the special case of F minor free deletion, the simplest case that is not yet understood. And it is interesting to see whether every problem from this family can be also is also like tractable in the sense of constant factor approximate kernelization. While our algorithm relies heavily on geometry of plane graphs, every family of graphs that exclude some minors also enjoys some topological structure which might be leveraged. In particular, graphs of bounded genus also have some convenient structure, so some techniques might be generalized to them. All right, then let me finish with this. Thank you for watching.